In order to set up the spectral check measurement, we should connect the FOP-UV fibre bundle to the spectral check optic, holding it in place using the grub screw. If the fibre bundle is already connected to the IDR, that's fine. If it isn't, then we should go to the software and initialize in the spectral check configuration and wait until the motors have stopped moving before fitting the fibre bundle. And in doing so, we should fit it in, rotate it slightly to engage it within the slit, and hold it in place using the grub screw. The CL6 calibration standard can be connected to the 605 constant current power supply, red and black cables, and fan. We ensure the 6.3 amp current is selected and we can power the source on. And finally, we need only adapt the spectral check optic to the DAR of this CL6, and we are now ready, having waited for a lamp warm-up time, to perform measurements to calibrate the system. Benman Plus from the desktop. Double click on Benman Plus, and we are presented with the option of 4 configurations. We are performing now the measurement of spectral check, so we double click on spectral check to initialize in this configuration. Where the fibre bundle hasn't been fitted to the monochromator, one must run this configuration and wait to the end of the procedure before fitting the fibre bundle. This will take some time as the turrets, order sorting filter wheel and motorised slits are sent to a reference position. We can now go to scan setup, or follow simply the shortcut to perform the calibration measurement. Now in general, I would recommend that when one does a calibration that one selects a large number of scans, for example, say 10 scans, and allows the system to run for the duration required. Running this from the on time of the lamp, one can say for example that the first 5 scans are during the warm-up of the lamp and will be discarded, and the remainder we can take an average of them to ensure that no noise gets through into future measurements, because if there's any noise or instability in the calibration measurements, that will be seen in all results that you perform. Just to note that the custom wavelength file spectral check is selected and will always be selected unless it's been changed. The scan range is 200 to 1700 nanometers. For the time required, let's take 3 scans. Just check in advance that data correction is not selected. Data correction is calibration factors applied. Now we are trying to calibrate the system, so it must not be applied. But the other auto range and zero calibrate must always be selected out of note. Then hit new scan. The system will proceed to do a zero calibrate procedure, in which case a shutter is placed in front of the entrance slit so no light gets into the monochromator, and the dark current and ADC offset is determined for each detector. Here we're using all 3 detectors, so 3 sets of results will be returned. And then the scan will proceed from 200 nanometers to 1700 and repeat 3 times. And we will watch the scan commence, then pick it up at the end of the scan. So the zero calibrate results are in, with dark current and ADC offset for each detector being recorded, and the system is scanning. One can hit this shortcut button in the top right hand corner to hide the scan window to see the results where required. Now we are reaching the end of the 3rd measurement, after which we can apply data correction to move forward and do measurements of a source with correction applied. I will switch off the 605 constant current power supply, and we can look at the measurement results. We can see I've hit right click logarithmic axis to zoom in on the detail across the wide dynamic range of this measurement. We can see at 400 nanometers we swap detectors from the photomultiplier with high sensitivity, which is getting near to its 100,000 or near to 100,000 nanoamp limit, and we move to the silicon photodiode, and then at 1050 nanometers in fact we move to the InGaAs photodiode to avoid the long wavelength region of the silicon detector, which is sensitive to temperature. And we continue with the InGaAs photodiode, and you can see the responsivity of this diode is reducing towards 1700 nanometers. We can see a few interesting features, some absorption features from the fiber and the hydroxyl absorption feature of the quartz fiber, which really does attenuate the signal significantly. We can say that perhaps the first scan was taken as the warm-up scan, so we could go to analysis, delete spectra, for example, to delete the first measurement. If I had done 10 measurements and took the first 5 to be the warm-up period, I would have deleted the first 5 to leave the remainder. And I can go back to analysis, spectral average, to take simply an average of those results. And finally, analysis, delete spectra, to delete the original data, so I'm left with the average, which I will save in the spectra folder. SC is my code for Spectral Check to identify the type of measurement directly, and this is the CL6 calibration lamp we are measuring. Of course, you can determine your own naming structure. To apply data correction, one goes to Scan, Data Correction. The certificate file is the true output of the lamp. The calibration folder contains all of the calibration files, and for the spectral check and indeed the infrared measurement, the extended calibration file should be used. The units of this file has been provided as signal in arbitrary units, so that where we want to look at a measurement result, one doesn't confuse it with an actual absolute irradiance measurement. The system file is the one that we've just done. We can calculate calibration data. Data correction is not selected. Do we wish to select it now? Yes. And I recommend saving to file in the calibration folder, SC, and today's date, 28/05/2014. And now we can return to scan setup. You will notice that in advanced, data correction is now selected, so calibration is now applied, and future measurements will be provided in signal in arbitrary units. Now, we are now to set up a light source for measurement. Having calibrated the system in the spectral check mode, we can now proceed to measure sources under test. I have mounted the spectral check optic on a post-mounting system. The source, this MR16 source that I'm measuring, has been mounted in a lab jack. Sometimes it is difficult to find manners of holding samples, and this is a perfect example. A lab jack is a useful manner with which to be able to adjust the position of the sample, but one must be very careful about the orientation of the sample in terms of where the peak intensity is directed. It should be towards the input optic. But for this measurement of spectral check, this is a relative measurement, so we're not really concerned about that for the moment. In the spectral check measurement, we really want a maximum signal to get the best result. However, I recommend a measurement distance no less than 200 millimeters, really from a concern that if the source emits significant amounts of heat, we don't want the fibre bundle to be damaged with the thermal load, so 200 millimeters is a reasonable consideration. So we can adjust the distance to 200 millimeters, and we will now look at the software using the alignment utility to optimize the position the height and the lateral position of the sample to get a maximum signal. Now we go to the Utilities menu and select Alignment Utility. We can set the monochromator to a wavelength at which the source emits light. For a white light source, 555, the peak of the visible green wavelength is suitable, as in this case here. Of course, if you're measuring a source outside this region, for example a UV LED, a blue LED, then you should select a wavelength appropriate to the source. If you don't know which wavelength to use, one can make an approximate alignment, do a quick measurement to measure where light is emitted, and use that information to perform a refined measurement. So we've input 555 nanometers and hit go, and the monochromator goes to that wavelength and will report the signal measured. We wait for a few seconds for the amplifier to range, and then I can adjust the height. See, we've got an increase, and then the lateral position. We should also be careful of the orientation of the sample. The axis in which the peak emission is output should be approximately constant with the optical axis to ensure that we are measuring the peak signal. But again, we need not worry too much for this spectral check measurement, which is really relative. So I think that's okay, and let's just do one scan, new scan. We see that on the y-axis we have reported the signal in arbitrary units. Data correction is applied, and we will have a correct shape, albeit not correct around the vicinity of the hydroxyl absorption at 1380 nanometers, but that is immaterial. For all we want to find out here is where is there light, and we will look at the results at the end of the scan. Now the scan is completed, we can look at the results presented initially on a linear y-axis. We can see for this source, quite an unusual source, a 405 nanometer pumped LED, the LED emission at 405 nanometers and the resultant phosphor emission. On a logarithmic scale, right click, logarithmic axis, we can see from the noise, we can measure in the UV, up to the peak we're looking at 10, 100, 1000, 10,000, 100,000, a million times or more difference in signal. There's clearly no UV in this region here emitted, so below say 350 nanometers, but certainly there's some small component up to 400 nanometers. In the infrared, we can see again we've gone from the peak of the phosphor emission around 650 nanometers, we've gone 10, 100, 1,000, 10,000 in signal down to the infrared. In the first estimation, to determine whether one needs to measure in the infrared or not, putting one's hand in front of the source, if you feel heat, there is infrared to measure. Otherwise, as seen here in this measurement here, there is very little to consider oneself with, to concern oneself with. The Spectral Check automatically reports the blue light integral and the retinal thermal integral. If the ratio of the two, retinal thermal divided by blue light, is less than around 34, by theoretical analysis one can effectively classify retinal thermal as exempt, provided blue light is exempt. And there's some notes in the PSL folder guiding one through this procedure. And we can of course save this result, a spectral check of my LED, and we can use this, as I say, to decide which regions we need to consider. Effectively, in the following measurements of irradiance, we will either do 300 to 1100 as a standard measurement, or 200 to 1100 nanometers in the irradiance measurement. Given that there's no mission below 300 nanometers here, I will decide to do a measurement from 300 nanometers up only, so obviating the need to calibrate with the deuterium irradiance standard. Where we suggest that there is no emission above 1100 nanometers, we need not perform measurements in the infrared configuration.